Hi guys, till now what we saw is application of hydrogen bonding. Alright, so significant bond in biological system. We saw it in DNA, we saw it in cell membrane, we saw it in enzymes, and then we also saw how it helped in orientation of water in varieties of situations. Alright, now here what we are going to see, we are going to talk something about hydrogen bonding helping organic reactions. All right, now let's check into it. All right, in scientific field or in research, whenever we are setting up a reaction, two factors linger into our mind. Now these two factors for organic reactions are electronic factor and steric factor. Which of these two are going to dictate the organic reaction? So I've been very lucky that I got exposed to a type of reaction in biocatalysis where the main theme was steric versus electronic. Two groups were chosen. One group of alcohols were sterically hindered for these reactions. Other group of alcohols were electronically favored. Alright, so these two groups were chosen. For this reaction, ethyl acetate was chosen as the ester, and this ethyl acetate was transesterified with those alcohols which I mentioned already. Just would like to mention over here that this work got accepted into an international journal known as Biotechnology Letters from UK. Alright. Prior to getting into this reaction or discussion, Gaurav is going to explain something about those alcohols regarding their electron withdrawing or electron donating capacity, that is electronic factors, and about their steric factors. Alright, let's understand what Gaurav has to say and then we'll carry on for the discussion.
Hi, I'm Gaurav. So I'm going to talk about the steric versus electronic factors about the substituted ethanols which were used in Ankur's scientific work. Here we have one group of ethanols and another group of ethanols where we have bromoethanol and chloroethanols. Both are EWGs, also known as electron withdrawing group. Here bromoethanol is sterically more hindered than chloroethanol because the size of bromine is greater than chlorine. Whereas in this case we have these two ethanols where both are EDGs known as electron donating group, where butoxyethanol is sterically more hindered than methoxyethanol because of the bulky butyl group. In this case we have these two ethanols which are comparatively stronger EDGs than the other two. Here, diethyl aminoethanol is sterically more hindered than dimethyl aminoethanol. Further, my colleague Ankur will carry on.
Thanks, Gaurav. Now let's carry on the discussion on conclusion that we draw from reactions that we had carried out. Now the experiment performed were using these alcohols, of course, as nucleophile, ethyl acetate as the substrate on which these nucleophiles would be reacting. Enzymes were the catalysts. We used lipase enzymes. Two lipase enzymes were used, Candida cylindricea and porcine pancreatic lipase. These reactions were transesterification reactions. Now regarding conclusion, steric or electronic, what do we bet on? The conclusion was that it was dimethylamine derivative, chloro derivative and methoxy derivative of ethanol which reacted faster and towards higher conversion. These reactant gave product with conversion of around say 85 to 90%, whereas its counterpart one which was sterically hindered but electronically favored, gave percentage conversion to the extent of around say 25 to 35%, which were very low. So can conclude that these reactions were sterically favored. Now let's move towards isosorbide. Isosorbide is yet another molecule which has got lots of significance as its source is from cellulose. Just hydrolyze cellulose, you get glucose. Once you get glucose, deglucose, do reduction, you get sorbitol. Remove two molecules, dianhydro, two molecules of water from sorbitol, you get isosorbide. After that, and again bring hydrogen bonding into it. Alright, this is the process which Bhumika is going to explain.
Hi guys, I am Bhumika and I am going to talk about isosorbide synthesis. Glucose is obtained by acid hydrolysis of cellulose, which is a renewable source. Phosphoric acid, sulfuric acid or hydrochloric acid is used for this purpose. Hydrogenation of glucose is done in presence of nickel catalyst, from which we obtain sorbitol, and on dehydration of sorbitol we obtain 1,4 sorbitan, and on further dehydration we obtain 3,6 sorbitan, and the ultimate product we get is 1,4,3,6 dianhydrosorbitol, which is also known as isosorbide. Isosorbide is biodegradable, soluble in water and is classified as glass, that is generally recognized as safe. There are ample applications of isosorbide which Ankur would be dealing.
This is just the carbon skeleton for better understanding of exo and endo hydroxide. Now as we check out over here, this is what is exo hydroxide and this is what is endo hydroxide. Alright, so this is our first carbon, second carbon, third carbon, fourth carbon, fifth carbon and sixth carbon. To fifth carbon is attached the endo hydroxide. Alright, and when we come back here to the second carbon is attached exo hydroxide. Now this gives an idea that since this hydrogen, if I come closer, this hydrogen is hydrogen bonded with this oxygen, it is also hydrogen bonded with this oxygen, owing to which what happens is this becomes active. Alright, now when actually I put in all hydrogen and show you, you would find that how it is entrapped inside, and that's the reason why it is called as endo. Alright, this is how carbon skeleton of isosorbide looks with all hydrogen fitted in. Alright, now this, as mentioned earlier, is endo hydroxide. This is exo hydroxide. I already explained the hydrogen bonding. This is just to show how it now is there entrapped over here in this vicinity, so it is endo, whereas this is absolutely free outside. Alright, now what I intend to show you over here is, now this OH is active, this OH is also active, so two hydroxides at two extreme ends. This is what is required by a building block of a polymer. So this also acts as a very good building block for varieties of polymers also. Alright, so this is what we would be seeing later on. Alright, and all this happens purely because of hydrogen bonding. In the reaction which I presented earlier, we found that the nucleophile were better if steric hindrance were less. Alright, now here again in case of isosorbide also we were expecting the same thing. So the endo which was there, endo hydroxy which was there, we were expecting it to be lesser reactive or weaker nucleophile. But what happened? Because of hydrogen bonding, again hydrogen bonding, mind you, because of adjacent hydrogen bonding, this nucleophile or O also became very active. Alright, again hydrogen bonding comes to play, owing to which isosorbide has been used for varieties of products. Right from pharmaceutical, it has been used as a building block for vasodilator. It has been used as a polymer now, since both endo-exo hydroxys can be used as nucleophile, so it can form polymer chain on both the sides, so would form polymer, and these polymers are being used in automobile industries. It is being used in packaging industries, biomedical devices, and lots more to come. Why? Because isosorbide is derived from natural product, that is cellulose, renewable resource. It's a biodegradable product. At the same time, it is GRAS, GRAS, generally recognized as safe. Alright, so with these properties, this could be building block for many more products. And mind you, again I bring your notice to hydrogen bonding. So hydrogen bonding makes a sterically hindered hydroxide also a good nucleophile. Alright, this was my concluding video on hydrogen bonding. Alright, would be talking about some more aspect in my next video. Keep viewing. See you then.